So today I will focus really on proving these two theorems from model theory, which was used in the first lecture in the proof of Axe and Hilbert-Nussdalen-Satz. So let me call them used Axe's theorem. So it says that if this phi is sentence in the language of rings, then it is true in complex, it is satisfied in complex numbers, it can only if it is satisfied in algebraic closure of a finite field for infinitely many primes, which are the cardinality of this finite field. True here. Many numbers E. And the second, which I very quickly showed last time, but I will repeat today. Was used for Hilbert-Nussdalen-Satz. Was saying that any extension of algebraically closed fields is elementary.
Isn't it enough for only one prime?
Then it's not true. For example, the statement 1 plus 1 equals 0 is true for 1 prime, but is not true for C.
Yes. But isn't it true that algebraically closed fields are elementary equivalent?
No, I will tell you. Of the given characteristic.
Okay.
So that's the only invariant. Yeah, it will come actually very soon. An extension of algebraically closed fields. It's elementary. Yes, actually numbering maybe is a bit unfortunate. First I will show this theorem, then actually I will show that if we fix characteristic, the theory is complete, and using this I will show that. Okay? So, I think from last time a bit, root of the second one. So we take extension Fm. We take some extension as in the statement, so extension of algebraically closed fields, and of course our aim is to show this is elementary. So let me recall, this means that for any the sentence also okay, for any our sentence alpha but with parameters from F. So we allow parameters. So in other words, it is LIF sentence. We want to show this group. This is what we want. And as it was last time, we take cardinal number kappa, which is greater than cardinality of the bigger group. So let me now not repeat too much about. Okay, and then there was a problem. So problem 14 for users. That in this context, sorry, I'm trying to do it first. Sorry. And now by F upward column low and high. There are elementary extensions. Such that they have cardinality kappa. So in particular, since elementary, it implies that they are algebraically closed fields. So now I'm saying that this problem number 14 says that in this context you should be able to show that because they have the same big cardinality, big respect to this field F, they are extending. Yes, they are both extending this F. Because this one extends F, this one extends M, and M extends F. Okay, and they have both big cardinality with respect to this F, and they are both algebraically closed. So all of it should imply that they are isomorphic over F. Okay. So let capital Psi be this isomorphism. Yes, this means that restricted to F is identity, so each element of F doesn't change it. So we can now look at this whole situation. We have here the smallest field, this capital F. This extension, which we now can extend as a map, inclusion, elementary extensions, which we also extend as maps. Yes, so this we want to show is elementary. We know this ones are elementary. And here, this Psi. So I'm saying the diagram is commutative because Psi is over F. So kind of these are inclusions. So here each element of this F goes to the same element, here the same, and by C also the same, because it fixes pointwise capital F. So because of this, and now we take this sentence alpha, okay, so we have our sentence alpha parameters F, so it means it is of the form alpha is of the form some C, so 1, and where C is a formula without any parameters, but it has three variables, and we flag these parameters for three variables. This is always how formulas with parameters are constructed. Yes, we didn't write everything, but I'm saying that any sentence alpha, LR sentence alpha, with parameters from capital F is of the form some formula without any parameters with three variables x1, xn, and then instead of these variables we put parameters from capital F. Maybe there are no such, maybe n is 0. Maybe there are. Okay, so now we are checking that F. Okay, so we want to show this. So we will just show that this is equivalent to this. So if F, if in F this is satisfied, okay, this is satisfied in F, we cannot leave because of elementary extension. It is satisfied in F prime. So now there is this moment when it becomes important that this one preserves parameters from F. So now F prime in general, such a thing is true. Sorry, F prime, not M prime. Because isomorphisms present the truth, that was this lemma. So this is isomorphism presents the truth. Yes, but because this C is over F, this is 1 up to the end. And finally, we can yes, so first we go here. Here to here, that was the first if and on leave, then from here to here, this was the second if and on leave, and then we can go down by this elementary extention. Okay, so and because this parameter exact from F, here of course, and this is true formalized to here, the parameters from F, if and only if it's true here. This, and because this T1, Tn, since they are in F, they are also M. Okay, so now that this is equivalent to this. Which was exactly what we wanted to show here. Okay. Which I said last time, but maybe a bit too quickly. As one should be careful that just this we also to reserve capital F. Without this, it would not work. Okay, so two main ingredients. One was this Skolem-Bodenheim to find these big extensions, which is basically compactness theorem. It follows directly from compactness theorem. And second ingredient was purely something about algebraically closed field, that they become isomorphic over this capital F. Actually, there is a general property of model theoretical property called Aleph1 categoricity. Okay, so theory is Aleph1 categorical if any models of cardinality Aleph1 are isomorphic. Actually, by general results, it implies that any models of any uncountable cardinality are isomorphic. Very general theorem. If they are isomorphic for some uncountable, they are isomorphic for all. This is Morley categoricity theorem, right?
The start of model theory is considered to be
yeah.
beginning.
Okay, well, since I'm Polish nationalist, I would start with Tarski, but maybe this serious one, yes. Yes, true. It is in this book of Sachs, I think. It is nicely explained. Okay. Huh?
Can you say again what was the...
Morley. Okay. Morley jak Morley rank, yes, the same Morley.
I was asking for the theorem.
Categoricity theorem. It doesn't, this is not category theory, it's the name that theory is categorical. In general, theory is alpha categorical if two models of cardinality alpha are isomorphic. Okay, and actually, Aleph zero categorical theories are quite special. It means they have very, very little formulas, kind of. And then the other type is this Aleph 1 categorical, which means doesn't matter which. So actually, this proof can be repeated with some care, I think, that any Aleph to show that, okay, any complete Aleph 1 categorical theory has this property, which is actually called model complete, which I will later define. Okay. So my point was, okay, that there was one general ingredient and one specific ingredient, but the specific ingredient can be also generalized. But on the other hand, there are not many theories such. If you think about the, okay, categoricity theorem is true in countable language. Okay, that's the thing. I guess, because if you think about theory of vector spaces, it's the same. If you have big cardinality, then two vector spaces are isomorphic of the same cardinality. So that's another example. Okay. So now we are, so this MT2 is proved and discussed. Now we are aiming towards MT1. Okay, so definition. It appears so let some question or
The statement of Morley that it is.
But now with this language I would like to check what's the okay, definitely if language is countable, then if a theory is categorical in one uncountable cardinal, is categorical in all uncountable cardinals. Okay, so ACF, we just give a name. Let ACF, it is very commonly used, algebraically closed field, denote the LR theory of algebraically closed fields. So you were writing axioms in problem session. So here we don't specify the characteristic, but if we put the subscript, then we do. So now, okay, let P be a prime number, or P equals 0. Okay, usually P is just a prime number, but here let us also include possibility that P is 0. So then ACFP denotes the theory of algebraically closed fields of this characteristic. Okay, so of course one can ask now about completeness. So this one is not complete as we discussed, because fields of different characteristic cannot be elementary equivalent, but the next theorem says that it's enough to add characteristic. So in other words, this ACFPs are completions of ACF. So theorem that for such a P, ACFP is complete. Okay, so definition was, I'm recalling definition, that for all R sentences phi, we have that phi is a logical consequence of phi of ACFP or negation. But in the proof, we will use this criterion from one of the problems. So, proof. We take two models and we want to show that they are elementary equivalent. So let us take two models. So just two algebraically closed fields of characteristic P. So now it's really shorter to use such a thing than to say algebraically closed fields of characteristic P. That's why people like to use this notation quite a lot, if they are model theories. Okay, so now by problem 11, it is enough to show that they are elementary equivalent. Yes, we discussed it. Oh. And it's similar to this, and actually this also can be generalized to more general context. It will be similar kind of diagram. So let F1 be the prime subfield, of K1, and let F2 be the prime subfield of K2. Yes, huh? Oh, Q. Okay, so yeah, exactly. So I will just say, but the point is it is the same, basically. Okay, so since, yes, what you are saying, since characteristic of F1 is P is characteristic of F2, then they are isomorphic. If you want, you could say equal, but really isomorphic. So as you said, this Fi is Fp if P is greater than 0, or Fi is Q if P is 0, I is 1, 2, yeah. Okay, but we cannot use them because, of course, they are not algebraically closed. But this K1, K2 are algebraically closed, so then they're okay. Then also, if two fields are isomorphic, then algebraic closures are also isomorphic. And of course they are either FP-alge or Q-alge. And we have that this one is subfield here because it is algebraically closed. So must contain any algebraic closure of any subfield, and the same. Okay, and now we can repeat at this moment, we can kind of repeat this argument. So by theorem, but using the theorem, so by MT1, we have that in both cases, these are extensions of algebraically closed fields, so they are elementary. And now, so it's even a bit stronger, that's something we want to use. In particular, we have that the theory, so the theory of K1, since this is elementary, is the same, alge, is the same as theory of F1 alge, and this is the same as theory of F2 alge. This is again the statement that isomorphism the truth. And here again we go down, up. Okay, here we went down, here was isomorphism, then we went up, then now we are going up. Same as theory too. And of course this is so. This is the same, which means exactly that they are elementary equivalent. Yes, a little picture here is that we went like this. And somehow traveled with the truth of sentences. So here the diagram was not complete, but it was enough to travel with any sentence we wanted to get this completeness. Yes, now everything is quite easy. Yes, so here, there is some obvious way to generalize it, which I didn't prepare. So I think the statement is if theory has this property, that any extension of model is elementary, and if it has a unique up to isomorphism prime model, there is such a notion really like here. So here actually prime model would be this FP arch. This is like prime model of algebraically closed fields. Then it is complete. That would be the general.
If categorical is some infinite cardinal plus no finite models. Complete.
Is it? Okay. That implies that, okay, maybe. But this is stronger. Okay, but this is stronger. This would use this argument. Okay, this is, I think, something weaker. That model complete and having prime unique. Okay, and having unique, I guess, comes from primeness. So I'm having prime model over empty set. I guess it feels like a weaker assumption than categoricity. So I think it's okay. Yes, but I didn't prepare this part, so I'd rather. Okay. So now this theorem. MT2. Okay, good. So I will state it here. I will state something more general, which is called Lefschetz principle. So let's phi be an LR sentence, and okay, so in MT2 we had two things, MT1, sorry. Now I will actually write 4 equivalent conditions. The first one is, instead of infinitely many, will be almost all, which means all except finitely many. All, maybe totally all except so maybe this is what you wanted to say, that's because you said 1 prime, so you can also say other things, not infinitely many, but equivalently more than infinitely many, all except finitely many primes p. So now p is a prime, not 0. So sorry for this possible confusion, but I'm saying what is it? Primes p, we have fp alge models this phi to exact statement from here for infinitely many. Yeah, which kind of, by this statement even, it would be impossible that for, one could wonder whether it's possible that for infinitely many primes p, phi is true, and for other infinitely many not phi, but by this equivalence it cannot be true. So something like this I'm stating, for infinitely many primes p, fp alge, have the same. Phi is a logical consequence of ACF0. Okay, I could also say then for infinitely many primes is a logical consequence of this ACFP, but it would be too long. Or it is true in complex numbers. Okay. So of course some things are obvious. This is just weakening of the condition from 1. Now the main point, implication from 2 to 3. Okay. So we assume 2 and we want to show this. So now since ACF0 is complete by the previous problem, by the previous theorem, now we have a problem, problem 12, second part of problem 12 was saying that in complete theories this is true if and only if we add this phi to the theory, then it is still consistent. Okay? It is complete. It is enough to show. So again, this is how compactness theorem will be used really, to show that ACF0 extended with this phi is consistent. So by compactness theorem, completeness theorem, we need to show that it is finitely satisfiable. Yes, so recall again what's the situation. We take theory of algebraically closed fields of characteristic 0 and a sentence which is true in infinitely many FP alg. And we want to show that such a thing is consistent. Okay, so probably one can already imagine, but let's do it precisely. So we take here T0 finite, and we want to find a model of this T0. Okay, so what is really ACF0? Let's write it precisely. For n greater than 0, let Vn be the sentence saying that it is not true that if we add 1 to itself n times, then we get 0. So then ACF0 as a set of sentences is ACF and all these Vn's. Yes, that's what we need to add. So ACFP is, of course, ACF for P prime is ACF with one sentence. Here we have to add infinitely many, but that's actually the reason this will be enough. So T0, since T0 is finite, there is some big N, capital N greater than 0, such that T0 is contained to this phi1 up to phi capital N. Huh? Yes, yes, then take a bigger prime, and that's the model, okay? And probably will be also time for a break. But still, let me finish. So since FP alg models our original phi for infinitely many primes p, as you said, there is such a prime greater than n. And then, of course, so it even models the whole ACF and this phi yes, okay, still not this, but so this one is satisfiable. Yeah, we found a model for any finite subtheory. So theory is finitely satisfiable, and this may be a good moment for a break before two last implications. Okay, so let's have a break.